Yes. Yes, is it Evelyn?
Yes.
Evelyn, here you go.
Thank you.
Yep. Everyone, pass around attendance again. Okay, so for our quiz at the end of class today, make sure you draw skeletal structures, Lewis structures, condensed structures, isomers. If you can do all that, you'll be fine. All right? For resonance structures, just remember what I told you. You could move lone pairs and double bonds to a different place if you don't break the octet rule. All right? So hopefully we got enough practice by doing the homework. But alas, I can't go over that now. We have to start talking about alkanes, chapter 3. Okay? So last time we talked about the functional groups. We stopped at diphosphate. Okay? Now let's talk about amines. So amines. Amines, anything with nitrogen in it gives you a headache. I mean, ammonia, urea, uric acid, they're all excreted out of our body. Very smelly compounds. And you have high levels of them in your body. It probably will cause you to feel sick. Okay, so that's why we excrete them out of our bodies. All right, amines is the most simplest of the nitrogen compounds that has bodily function. All right, so these dash and wedge lines, they just mean they're different connections to carbon atoms. Okay, and the nitrogen right here can also be bonded to other stuff here in a lone pair. All right. So we named these with the ending amine. Okay, so like methylamine, benzylamine, triethylamine, stuff like that. All right, so this compound, the simplest alkylamine, methylamine. All right. So remember, if they don't have a dash with their ending name, they're one word, like methylamine. Okay? All right, so let's go over a few more functional groups, and then we'll start talking about organic molecules, okay? Or just naming organic molecules. All right, so that's amines. You also have the amine variant. Amine, though, is slightly different. Okay, with amines, you have a double bonded N here and a lone pair right there. All right, amines also have unique functions. We'll talk about this guy, not in this class, but if you're in 18B, we'll talk about that then, okay? There's no ending name for amines. Okay, so the simplest one I can give you is this one. CH3. This has a special name because it's based off another compound. So this is called acetone amine. So see how it has no really specific name. Its name is given off by acetone, where this molecule, if there was an oxygen instead of a nitrogen, that would be acetone. So we substituted there for an amine. That's why it's called acetone amine. Okay? All right, nitriles. So this is not the same as cyanide. Cyanide is the anion, but if it's connected to carbon atoms, that's called nitrile. And we have some specific ways to name it. Here's an example, CH3, C triple bond N. That's called ethane nitrile. All right, so I probably won't test functional groups until much later. So don't worry about knowing the functional groups yet, but be familiar to the kinds of functional groups we'll talk about as I go through each chapter, okay? All right. Next, we have a diol. All right, smelling compounds, the ones with sulfur. All right. So the SH group is the diol. Okay, so diol. All right. And whenever you have these compounds, they're quite smelly because of the sulfur atom. Methane diol. It's one example here. Okay? All right, sulfide. Sulfide, it's like a diol, except now you have two carbon groups besides the sulfur. So sulfide will look like this. S, C, boom, boom, like that. All right, sulfide, no hyphen next to it. So if we have a sulfide, we name it dimethyl, because there's two of them, two CH3 groups, and then a space between sulfide. All right, so sulfides, they're more important on DNA. No, not DNA, sorry, proteins. So when we have sulfides and proteins, they form the linkages between the protein chains, and that's a disulfide bond. Okay, but sulfide is the key component there. All right. Then if we oxidize the sulfur, we get sulfoxide. Okay, so anything with sulfur, you gotta be careful. If you put hydrogen peroxide in there, and oxidize the sulfoxide. So a very vigorous reaction. All right. So sulfoxide is a little weird. You typically would draw this as a double bond, but the bond is so long that it's really not considered a double bond. It's considered a single bond. So that's why we draw it like that, typically. But in most places, you won't see it drawn as like that, as like in Gen Chem, and that's because of the rules you learned about formal charge, minimizing the formal charge. All right, so that's sulfoxide. Okay, so if you have, so this is a common solvent that we'll learn about. Okay, so I will abbreviate this solvent as DMSO. All right, so this is what we call DMSO. It's a common organic solvent. All right, so this is called dimethyl sulfoxide. And it's a common solvent we use in organic for synthesis. Okay? Thing about DMSO though, it's hard to drive off, so it's very hard to evaporate. So you have to use DMSO. You want to extract your product into some other solvent like ether that evaporates very quickly. DMSO is hard to get rid of. All right, so that's a sulfur derivative, on major sulfur compounds. There's another one called sulfone, but we hardly ever encounter them. Are any questions so far on functional groups? Seem familiar? Maybe it's not because it's first time taking organic. All right, but hopefully you recognize some of these bonding patterns here. All right, aldehyde. So aldehyde is where the double bond O comes at the end of a compound. It can never come in the middle or start in the middle because there's no hydrogens that can hang off with a double bond O. All right, so C double bond O, sorry about that, weird H. All right, so that's an aldehyde. It has an H attached to the double bonded carbon atom. All right, and the prefix, or the suffix here for the ending is al. So the most simplest one is formaldehyde, which is also called methanol. But I'll just give you this example. CH3, C double bond H. All right. So that would be ethanol. All right, it has a common name, acetaldehyde, which is one of the products during alcohol metabolism in your body. Okay. So alcohol gets converted to this first when it oxidizes in your body, and then eventually it will turn into probably some other. I think it gets turned to this compound, and it somehow gets recycled to your liver and stuff like that. All right, but don't quote me on that. All right, so that's aldehyde. Ketones. All right, ketones. You've heard of ketone bodies. So compounds like ketones can accumulate in your blood, especially if you don't have enough ketose. Okay, so bam. All right. So ketone looks like this, and then. So your body can also get energy by metabolizing these compounds. Even though they're not directly sugars, you can still break these down into several pathways to get energy. All right, like the keto diet. All right, so the ending here is one, O-N-E. It's not one, okay? It's O-N-E, own. All right, so the most common ketone is propanone. Another popular solvent here. This is commonly known as acetone. All right, and acetone, you probably, it's in a lot of products like nail polish remover, that or isopropanol. All right, so that's a ketone. All right, so see, we're going now down to more doubly bonded functional groups. All right. Carboxylic acid is the next one. All right. Bam. Okay. So carboxylic acid, the ending here, it still has acid in the name, but it's oic acid. Okay? So oic acid, like that. All right, so the most common one is acetic acid, but that's the common name. The more appropriate name is ethanoic acid. So I'll put this here, acetic acid, but the more appropriate name is ethanoic acid, the IUPAC name, all right? So we'll learn about those names later on, okay? All right, so a few more here. Ester. All right, so esters, they're in perfumes, very pleasant compounds. So aromas of fruits, oils, like so, they are esters. All right. And the abbreviation here is O8. Oat 8. All right. So methyl-ethanoate. That's found in like wintergreen. So very pleasant smell. The oil wintergreen, very like kind of refreshing, minty a little bit. All right. So very pleasant aroma. All right. Then, similar to the ester, you can have a dioester where there's sulfur instead of oxygen. So let's write that, dioester. So instead of a oxygen next door, it'll be a sulfur instead. Like that. So here we have the abbreviation or the ending diol 8. All right, so CH3, C double bond O, S, CH3. So this would be called methyl ethane Diolate. All right. So very similar to the ester there, but you have a sulfur instead. All right. All right. So the last three we'll do here have to do with nitrogen. And we call these carbonyl derivatives. Okay? So amide. So amide is pretty important because it's found in proteins and other compounds in the body. So it makes a big portion of biomolecules. All right, boom. And then we have nitrogen here. Oops, don't want to solve. Don't want to solve there either. All right, so amide is the ending name. All right, so our example, CH3, the simplest amide, well, it's not the simplest, but the simplest carbon amide right there. So eptan, so you say this epthanamide or amide, okay? Like that. So then carboxylic acid, but we have a halogen. So the most common one is acid chloride. There are acid bromides, but they're not as commonly used. And there's acid iodides, but they react so differently that they're never used at all. So except for some maybe niche cases, right? But acid chloride is the most representative of the acid halides. So that's why it looks like this. All right. And then we represent this as oil chloride. So it has oil name and then chloride with a space in between. So this group here is known as ethanoyl chloride. All right. Okay. So these are most of the functional groups. One more. Okay. So now, what if you had a carboxylic acid, but you drove off the water and brought two of those together? That's called an anhydride without water. So carboxylic acid anhydride. So anhydride means without water. Okay. So you have something like this. Bam. Boom. All right, and the name here, you're going to get, let me just move this over a bit. You get oic anhydride. And the most common one we use is this one. C double bond O, 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 CH3. So this is ethanoic anhydride. All right. And when we come to name these things, I'll explain more. But it's based off on how many carbon atoms there are. All right, so those are the functional groups. So take a good look. You will be able to recognize some of them that we go over during the next few months, okay? But now let's go over how to name these things, all right? Naming organic compounds, that's next. Okay, so one thing about naming is a very systematic system. So first you have the prefix. All right, this includes the name and location. And we call this the substituent, or maybe more commonly here, the branch. the name of the branch, okay? You have the stem. That's the rest of the compound, or sorry, that's the root of the name, okay? This includes the number of continuous carbon chain, all right? So you're going to count carbons in a row. Count 4 of them, butane, 8 of them, octane, etc. All right, and then lastly, you have the suffix. I did not want that. All right, the suffix. That's the name of the functional group. Like that. All right. So our first branch of compounds here, they're namely the hydrocarbons. So I don't know. They're not really that interesting, except we use them for fuel, lanterns, go hiking, oils, waxes, found in whale blubber. That's why whales are hunted, pretty much. And they're mainly found in fats, as you know, dietary fats, bodily fats, or fats used for cooking, maybe fuel, stuff like that, okay? All right, so we have hydrocarbons here. So hydrocarbons, we're going to break them down into several categories. All right. Here is the aromatic hydrocarbons. So these are most notably obtained through oil refining and stuff like that. You can get aromatics from biomass, but they're much more derivatized than simple aromatics. So yeah, it'll be a milestone if you can renewably get benzene from, say, a tree. Okay. Aliphatic is what we call any alkane that does not have double bonds in it. All right, so not aromatic. All right, so aliphatic, well, let me back up. Aliphatic is anything that's not aromatic. Okay, it doesn't have the benzene ring. So aliphatic is carbon and hydrogen atoms that make up alkanes, and it has 3 categories here of the hydrocarbons at least. So one is alkanes. All right, the other categories are alkenes and alkynes. All right, alkenes have generic structure. We probably know this. Double bond. And then alkynes is the triple bond. Okay. And then alkanes, okay, you have 3 different groups here. All right, straight chain, branched, and last one, cyclic. All right, so we'll go over alkanes right now, just alkanes. Alkenes, alkynes will come later. And then we're going to start talking about straight chain and branched. Cyclic is the next chapter, which is 4. Okay? All right, so that's our hydrocarbon outline there. So now let's start naming some. All right, so let's go over alkanes. All right, any questions on this chart? Pretty clear? Okay. All right, so alkanes. What are alkanes? Let's see. Alkanes only have sigma bonds. Okay? All right. So when we name alkanes, there's going to be a stem name. All right? So let's talk about naming them. So naming, straight chain, We call these normal. So sometimes these will have the N prefix for normal alkanes. All right, so an alkane will satisfy this formula: CnH2n plus 2. All right, so N is the number of carbon atoms. Okay, so every hydrocarbon will have, if it's an alkane, it will have twice the number of carbons plus 2 hydrogen atoms for every N carbon atoms. Okay. So, for example, say we have a straight chain alkane here. Some number of CH2 groups, N, and then usually the N's are capped with CH3. Okay? So here's my example. You just draw a zigzag line. Okay, that's terrible. All right, 1, 2, 3. All right, I want to draw a 16 carbon atom. Hopefully you do much nicer job than I did right there. Okay, so for alkanes, I want you guys to remember the first 10 names for alkanes. Okay, so up to 10 carbon atoms. So you want to memorize names 1 through 10. All right, so CH4, what's that? Methane. C2H6, ethane. C3H8. What about this one? Am I using your barbecue? Propane. Propane and propane accessories. All right. C4H10, probably in your lighters. If you guys, I don't know, if you lighter fluid, lighter, if you smoke, butane. And then when we get to C5, these alkanes start to become liquids. So pentane is a common solvent. Hexane, C6H14. Heptane, C7H16. And then octane. So octane and its derivatives, anything that has 8 carbons, that becomes useful for gasoline and the octane rating. Okay. C9H20 is nonane. And then these other two, C9 and C10, they have specialized uses in analysis, and sometimes in like chromatography, so chemical processes, not necessarily like solvents or other like main outside of the lab kind of uses. All right. So here are some, if you're wondering what C11 is, so I'll write these to the side. You don't need to memorize this one. C11H24, that's undecane or undecane. And then if you have something all the way up to C20, H42, that has this name, icosane. Anyone guess how many isomers this has? Maybe you looked it up. 366,319 structural isomers. Don't worry, I won't make you draw all of those. That's probably impossible. They probably use some algorithm to determine this. Okay, I don't think you can draw all of them. Maybe there's a team of people who did this. Okay, so this includes just the structural isomers. This does not include the stereoisomers that are also present, so that's even more. Okay? But if I do make you draw isomers, it'll probably be, don't have to draw all of them. You just draw a few of them. Okay? And it's usually on the lower end of the alkanes. Okay? Less than 10 atoms, carbon atoms. Okay. So are we okay with the names for 1 through 10? It kind of if you think like mono, methane, ethane, just remember that's kind of like 2, propane, 3, butane 4, and then we get to shapes like pentagon 5, hexagon 6, hepta, octa, nona, decagon, like 10-sided. Okay? All right. I don't think I want to go with this one. Yeah, so those are just the name. Be able to name, know these names. So when we name an alkane, we can understand the parent name. Okay? All right. So linear chains are straightforward. They just have this common name here. Nothing really complicated about that. Now we get to the issue when we have to name branches. When we have branched alkanes, substituted alkanes. Okay? So naming branched, or in parentheses, substituted alkanes. All right. So there's a few rules we go into naming these compounds. So it's a lot more complicated than just naming salts or ionic compounds or molecular compounds. The names are typically longer. All right. So there's a few rules we have to, or guidelines we have to know. So 1, locate parent chain. Okay. So this is the longest chain of carbon atoms. All right. This is the stem name. This is the stem or root name. All right. So this does not mean you count in a straight line. You just have to count carbon atoms in a row. And this can be in a straight line. It can be zigzag. It can go up, down, make a U-turn, whatever it does. Okay? So for example, let me just draw this compound. All right. So we have to find the longest chain here, which each point or vertice is a carbon atom. So if we just straight across left to right, that only gives us 5. So I think we can find a chain that's longer. So if we number right here, 1, 2, 3, 4, 5, 6, 7. All right, so that's the parent chain, or the longest chain here, main chain. So look at it right here. Once we got the 4, we made a turn. So you may have to turn corners. All right, so it's not always a straight line in this case. All right, so this would be a heptane. Not just heptane, because you have more carbon atoms than 7. It's a substituted heptane. Okay. Are any questions about numbering a chain so far? No? All right. So let's move on here. All right. What the... Okay. Now, let me put the star point here. If you have 2 parent chains are the same length. So what I mean by length is that they have the same number of carbon atoms, okay? You're going to choose the path or the chain, choose the one, okay, with more branching points. All right, what does that mean? Well, say you have two paths that have the same number of carbon atoms, and you don't know which one to pick. You're going to pick the one with the more branches, okay? So the more groups pointing out like a tree branch, okay? Let me give you an example. So say we have this compound, all right, boom, 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 versus this one. Well, I'm going to give you two numbering schemes here. All right, so say we number it like this: 1, 2, 3, 4, 5, 6. Oh, but what if I started from the bottom and then worked my way to the left, to the right, like this? 1, 2, 3, 4, 5, 6. So we have two carbon chains of the same length, but this one is wrong. So not this way. So not this one. Okay? Because if we look at this chain here, how many branches do we have? One, right? There's only one group coming off the main chain at the third position. So this is one branching point. But over here, we have two branches here, two branching points. So we have one at the third position and one at the second position. So two branching points there. So we would actually name this compound as, so I won't actually name it, but we're going to name as a hexane with two substituents. Branching points. Like that. All right. So that's one. Find the longest chain. Are any questions about finding the longest chain? No? All right. So let's go to point 2. I'll just draw a line after each point just so we separate them, okay? All right. We already saw how to number a little bit, but the second guideline here is number the atoms in the main chain.
By atoms, or do you mean the carbons?
Yeah. Number the carbon atoms in the main chain. Maybe I should just put carbons. So number the carbons in main chain. Thank you. All right. So how should you number them? There's a few rules here. A, start at the end, closer to the first branching point. Okay, so we have two examples I'd like to show. All right. So you can number it this way: 1, 2, 3, 4, 5, 6, 7. Or you can number it this way: all right. 1, 2, 3, 4, 5, 6, and 7. All right. So let's compare these two. All right. On the one on the left, right, the first branch appears where? What number? 3. Good. And on the right, where does it appear? What number? 4. Yes. Okay. So here, if we point to this position here, our first branch point is at 3. First branch point number 3. Okay? So this is what we call the lowest point of attachment. And let's give this abbreviation POA. Okay? But over here, this point is at 4. So number 4 here is first branch. Okay? First branching point. All right? So this is what we call the highest point of attachment. So that one, we don't do it that way. Okay? So not this way. So it's going to be this one on the left. Okay? That's how we number that one. Okay? So it's this very systematic system. All right. Are there any questions about the numbering scheme? Why we did it this way instead of that way? Yes.
Would we have like a situation where there's like a symmetrical end?
Yeah, we'll get to that. Yeah, that's we'll talk about that next. Okay, good. Now let's take a little breather here. Well, let's not. Well, we're first going to say, okay, wait, how do we name the substituents then? That might be a question that you might have. So let's talk about that. So let's naming substituents. All right. Branches. All right. So there's a few substituents we'll see. One with carbon groups, one with oxygen, and one with halogens. Okay? So alkyl is what we call substituents with just carbon atoms. All right. So an alkyl group, you might have heard this, an alkyl group, methyl, ethyl, propyl, those are alkyl groups. So any alkane, all right, not alkene or alkyne, any alkane attached to a longer chain. All right. So how do we form an alkyl group? Well, you have to lose a hydrogen in order to attach it to a chain. So it lost the hydrogen. Lost I don't know if it's AH or an H atom. Let's just say AH atom. Okay? You're going to add the ending. So you're going to drop the A and E ending of methane. And you're going to add the YL ending of eel. Okay? So, for example, if we have this group, CH3, that is methyl. What if it's CH2CH3? What do you call that? All right, what if there's just 2 carbon atoms in there? What do we call it? Not ethane, but ethyl, right? So methyl is when we substitute a hydrogen and we attach it to the chain. Okay. There's also alkoxy. Okay. So instead of a hydrogen being replaced, you're going to, instead of a hydrogen and that's it, you're going to replace the missing hydrogen with an oxygen. And that oxygen is directly bonded to the chain, okay? So, let's see here. Alkane that has AH replaced with oxygen, all right? So, for example, CH3, CH2, O, and that's where it's attached, right? So say that's where it's attached, is adoxy. Okay? So we add the OXY ending, oxy, because it's bonded through an oxygen atom, but it's not just oxygen. If it was just oxygen, we'll call it oxo. but it has carbon in it, so we have to use aldoxy or alkoxy. Alkane plus oxygen. Okay, are any questions about alkyl and alkoxy? Alkoxy is like, it's common too, in like fuels, or like liquid mixtures too. Solvents, yeah, so solvent mixtures. All right, so let's talk about the last one, halogens that we commonly see. So we have halogens here. All right, so replace H with an halogen, which is usually X. So halogen is X. That doesn't mean oxygen in this case. Okay. So we're not changing the ending now. Halogens, we just changed the prefix. So like, we add a prefix. Okay. So use the prefix halo. So no, it's not actually halo. You never say halo, right? Like the game. You're going to say whatever the halogen is. So what if it's fluorine? What would you say? Not fluorine, but fluoro, right? What about bromine? Bromo, yeah. So, yeah, I know, it's kind of silly, but... And drop the ending of the halogen. All right, let's do an example. I don't know if you guys know what this is, but this was used to fumigate strawberries before. I don't think they do that anymore. Maybe they do. Maybe someone's in agricultural sciences. So yeah, to protect your strawberries from bugs and disease. All right, so this is called bromomethane. And the reason why it was banned is because it's a carcinogen. So it reacts with DNA. All right. So anything that can add a CH3 group is called an alkylating agent, and it can actually react with DNA, and that root gets in the way of the transcription process during DNA replication, and then you have to go into DNA repair. Okay, so that's bromomethane. All right. So, but we don't. This also has a common name, so I'll just give it to you. All right. So this is commonly referred to as methyl bromide. That's another way you can call this, because you have a Br group there and you have a methyl group in there, so this is a common name too. So this is sometimes we say methyl bromide, but the proper name is bromomethane. Okay, so you know it's an alkane, that's why. All right. Are any questions about those substituent names? So get used to these names because we'll have to remember them when naming alkanes here. Okay, so we were on number 2. So let's go now to we're still on that category. So let's go to part B. All right. So now, what if there's a tie? Okay. So by tie, you can say, well, if it's symmetrical, and Catherine was saying, or, if you count from both ends, and there's a substituent at the second position of each end, how do you break that tie, right? So, if there's a tie, okay, what I mean by that is equal distance away from each end. So this is when the substituent, the branching point is at equal distance away from either end, okay? You're going to now use the alphabet to help you break the tie. So use alphabet Tization. Now, if it's truly symmetrical, it doesn't matter which way you go. You just choose one way. Well, there will be a way, but if it's truly symmetrical, it wouldn't matter which direction you're going in. Okay. So you're going to use alphabetation to decide how to number the chain. All right. So I like to abbreviate this as first in alphabet. That gets the lower number. All right. So what if you have if you have 3 or more substituents? How does numbering work there? Okay. So a special scenario here: 3 or more substituents. Okay. You want the lowest numbers for all branches. All right, so let's do a few examples here. So let's draw a few chains here. So carbon atom, ethyl group, then another ethyl group. Okay. So you would number it this way: 1, 2, 3, 4, 5, and 6. Not this way. Oops. No, what are you doing? All right, you wouldn't number it this way: 1, 2, 3, 4, 5, 6. All right, so this group here, 2 carbon atoms, ethyl. What about this group here? What we call that? How many carbon atoms is it? If it's coming off this 4th carbon, how many carbon atoms are on that branch? 1, right? So this is methyl. All right, what will come first in an alphabet? Ethyl group or methyl? Ethyl. So that's why we number it according to the left scheme here, the left picture. 1, 2, 3, 4, 5, 6. Okay? All right. Let's do another example where we use we have a similar hydrocarbon, but it's just 1 carbon longer. Boom, boom. Oh, yeah. So let's number this chain: 1, 2, 3, 4, 5, 6, 7. All right. That's the way we number it, not this way. All right, so we wouldn't want to number it backwards. All right, and it's for the same arguments as the first example. On the right structure, the methyl has the 3 position, the ethyl has the 5 position. You want to flip that because ethyl comes first, all right? So 3 ethyl, 5 methyl, heptane. Okay? All right. Are there any questions about the numbering there? We okay? All right. So, first, longest chain. Second, number the substituents. Have the lower number overall. And then 3, identify and number the substituents. Okay? All right. So let's do letter number 3 here. All right, identify and number substituents. All right. So, how do we number the substituents? Well, we look at the main chain and see at what point of attachment is it at. And that's the number, okay? So, assign number, okay, for each substituent by point of attachment on main chain. All right, so just look at where it's at on the chain, and then you're going to give it that number, okay? So one thing I want to point out is that if you have two substituents on the same carbon, they get the same number, okay? So substituents on the same carbon atom will have the same number. All right, so let's say we have this group right here.
Professor Andrew?
Yes.
So if you can scroll up a little bit, where we have the methyl and methyl, how do you determine which is which? Is it based off the carbon?
Yeah. So let's go back to our counting here. So methyl comes from which name?
The first one.
The first one. So one carbon. Ethyl comes from what name?
The second one.
The second one. All right. What if I have, I don't know, a butyl group? How many carbons is that? 4 from butane. Yeah. So they're from the parent alkane name, and you just drop the A and E, add a YL.
And then how would you count that on the chain? Is it just
Oh yeah. Let's go over that. Okay. So this is ethyl, right? So let's just give a different color here. 1, 2. And here for the methyl, here's a 1. That's why it's called methyl, because we're numbering the chain, the number of carbons that come off the chain. Don't include the carbon it's attached to, if that makes sense. Don't include that in the number. It's the chain that's branching. So it might have been helpful if I actually drew out these in Lewis structures. But just remember, each point is a carbon atom. So think about how many lines you drew away from the main chain. That tells you how many carbon atoms there are. All right, so ethyl here, kind of highlight it. 1, 2, right? So that's ethyl, methyl, 1. And if you just draw more than that, 3, 4, 5, it'll just be propyl, butyl, pentyl, respectively. All right, any other questions? Good question, man. May I clarify everything here? That's what I'm here for. Any other questions? No? All right. Yeah. Okay. All right, I guess I can't zoom. Anyway, so this is actually a common additive to fuel, a fuel mixture. So fuels are basically just alkanes in them, and they combust really well. That's why they're used for fuel. Okay, so let's number this. 1, 2, 3, 4, 5. All right. So let's number our substituents. At the 2 position, we have a what? Methyl. What about at the 4 position? All right, there's 2 substituents there, so you have to number them individually. You can't combine them. We'll learn how to combine them later, but there's another methyl there. 4 methyl. All right, are we done? Or is there one more? There's another one at?
Are they at 4 or at 3?
Oh, yeah. Isn't that 4? I meant to say 3. My bad. 3. All right, here's what we'll do. Let's add another carbon atom so I don't have to go back. All right, so let's erase that, that. All right, there we go. So we'll still have to change this one. 4, 5, 6. There we go. So 3 mouthful, 4 mouthful, 4 mouthful. All right. Are there any questions about those numbers? Nope. All right. So that's how we numbered them, okay? All right. Boom, boom, boom. All right. Lastly, 4. You're going to write the name as a single word, okay? So if you put spaces in there, don't do that. I don't know, in this class, I'll probably have to dock it, so don't do that, okay? So remember, single word, okay? So if there's any space in between, I'll assume you mean it's 2 words, so be careful, all right? So there's a few things we should know. Use hyphens to separate prefixes. Okay? You're going to use commas to separate numbers. All right. And then lastly, order the substituents in alphabetical order. Okay? All right. If identical substituents are present, all right, you're going to use a multiplier prefix. All right. I want to emphasize, though, do not alphabetize by these prefixes. Okay, so do not alphabetize by these prefixes. Only alphabetize by what the name of the branch is. All right? But I'll give you some examples, okay? All right. So let's do this first one. Boom, boom. All right. So let's first find the parent chain. All right. How many carbons do you think it is? Let me know if you when you found out what number it is. Or just yell what number you think it is. All right. What do we think? 8? Good. All right. Where do we start from? The right here. Yeah, you can start from there. 1, 2. So notice here, it doesn't matter which one you start from. You can do either. 6, 7, and 8. All right. So the reason we number it that way, right, is because as our point of first difference. At the third position, you have an ethyl. If you started on the other way around, your third position would be a methyl. So that's why we number it this way. Okay. So let's look at our substituents here. I'll just notate it for this example. Ethyl, methyl, and then here, methyl. All right. So now let's name the compound. All right, so you're going to find the numbers where they're at, put a hyphen, and then write the alkyl name. And then you're going to then separate each prefix with a hyphen, okay? Now, if there's more than one identical substituent, you're going to list them together with numbers and a comma, all right? So let's start. So what's the first? What should I write first? Ethyl or methyl? Ethyl. So 3 ethyl. All right. Now, what's my other two substituents? Are they the same or are they different? They're the same, right? What positions do they appear at?
4 and 6.
All right, so write 4, comma, 6. All right, what's the common prefix for 2? Not bi. Di. All right, dimethyl. So notice here, di is a counter. That's not actually the name of the substituent because there's 2 of them, okay? So di does not come before ethyl. There's a time when di will come before ethyl, but now is not the time, okay? Later. All right. And then what's the stem name of the alkane? Is it hexane, a propane, butane, dodecane? Was it? Octane. So put this at the end. So no spaces. So see here, no spaces. One word. Okay. So we'll do lot practice here, but it'll also be lot practice next week as well in lab. Okay. So now let's do another one.
Just to clarify.
Yeah.
You used dimethyl even though there's 2 numbers listed, but because there's 2 numbers, right?
Yeah. You'll always list the number though. So even though there'll always be a number for each substituent present.
It feels repetitive to me. I mean, I can see why.
Oh, but if you say dimethyl, where are they? Right? Yeah. So you have to be specific here.
Okay.
Yeah. Okay. Because if I put the 2 methyl, let's say I put one at 7. Well, that won't count. But maybe at 4 and 5.
Right.
You have to be specific here. They are 2 different compounds.
Like 4 and 6 methyl, that's not the same thing, right?
Oh yeah, no, it needs to die to indicate that there's two of them there. Yes. All right. All right. So this is to save us from saying 4-methyl, 6-methyl octane. That's why we put the di prefix in there, just to make it simpler. Or else these names could run off the page, if you know what I mean. Okay. Boom, boom, boom. All right, let's number this one. Okay. So let's see. Well, you probably want to start one of the ends, I would think, because if you don't, you're missing some carbon atoms. All right. All right, what do you think? What chain length is this? 10. So we're probably going to start at what end? The left or right to number it? Not the right. Let's think about it. If we do the right, we'll have a 4 before we get to the first branch. But if we go from the left, bromine appears where? That third, yes. So that's the tiebreaker. All right. So let's start naming. What substituent comes first? Bromo, ethyl, or methyl? Bromo. 3 bromo. All right. Let's see. Ethyl comes at 7, so 7 ethyl. All right. Then methyl comes at 6, so 6 methyl. All right. What's the name for 10? Decane. All right, are any questions on that naming, how we named that? These are like the extent of what you'll be expected to reproduce, okay?
And you go alphabetical, not numerical.
Yes, alphabetical, right. No, not numerical. Yeah. We got to remember numbering. You give the substituents the lowest number, but when you're listing the name and the substituents, it's alphabetical, not numerical order. All right. Well, I wish that was the end, but it's not. Okay? So now we're going to go to complex cases. All right? So we'll take a step further. All right. For complex cases, another step is necessary. Okay. So, what do I mean by complex? Well, if your branching point is not a linear chain, you can't name it as easily, right? Because we know propyl, methyl. So what if the branch is branching, right? Like an inception kind of thing. What if there's a branch within a branch? Okay, so let me give you two examples. All right. So let's see here. All right. So if we number this molecule here, you'll get 10 carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So far we've seen branching groups as simple alkanes as alkyl groups, right? But look at here. What's that 6? Is that a simple alkane? No. There's a substituted propyl group there with an alkoxy group. So we can't actually, this is what we call a complex substituent. Okay, so let's highlight this group here. Okay, so that's what we call a complex substituent. Let me give you another example. All right, I think I just wanted to be CH2. Oh, right. And then something like this. Okay? Yeah, 1, 2, 3, 4, 5, 6. All right. This is also a complex constituent too. All right, these are what we call complex substituent. All right, and the reason they're complex is because they're branched. We can't just call them as they are. You might have heard like isopropyl, isobutyl. Those aren't IUPAC, so we can't actually call them that yet. I'll go over that a little bit later. Okay, I'm going to teach you the way how to name it systematically first. Okay, so if we look at this example too, pretty much the same carbon chain, except you have different groups at the 6th position. Okay, So I'm going to show you how you name complex constituent. All right. So number 5. Name the complex substituent as if it were a normal alkane. Okay, it's not normal because we're numbering we're naming a substituent within a compound, so it's kind of not regular. Okay, so let me just give you an example. Example above, we would call that a substituted propyl group. Okay? And that makes sense. If we look at these, the number of carbon atoms in my box, there's 3 of them with something sticking out of the linear chain. All right? So I could count these. I'll show this in the example, okay? All right. So you're going to number the branch at the carbon where it is attached. Okay? So let me just expand on this a little bit. Attached to the main chain. All right? Now, here is where we alphabetize based on first letter of the name. Okay? This includes prefixes with multipliers. All right? So remember when I said di, tri, tetra, those prefixes don't count in alphabet? Now they do in the complex because that's part of the name. It's part of that substituent's name now. It's not like I'm saying there's 3 of these. All right? There's actually a different prefix system for that. I might get into that. I might not. Okay? So the multiplier prefixes, they do count now in these complex cases. Okay? All right. And to indicate it's complex, you have to enclose these names in parentheses. Okay? All right, so let's do some examples here. All right, using the examples we went over above, let me start with this first one. All right. Oh, wait, I forgot to say something. Oh, my bad. Okay. Well, that's all right. Let's just do it this way then. All right. Okay. Sorry, guys. Let me redraw this real quick because I copied it wrong. Boop, 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 boop. Stage 2. Yeah, it's like this. All right. Yeah. Okay. So let's go over this first one. Boom, 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 boom. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right. So how do we number? So first, let's number this. 1, 2, 3. Okay. So let's first write. All right. So this name right here would be called 2-methoxy propyl. All right, this is this whole group right here, okay? Because we have an oxygen atom with 1 carbon. That's called methoxy. But where does it appear at on that chain? What number? Number 2. So that's why it's called 2-methoxypropyl, okay? Now, if we look at the other substituents, at the 3 and the 2, those are methyl. So that actually, now the complex substituent will come first. So, how we name this? 6 dash parentheses 2-methoxy propyl. All right. And we're about the other 2 names. What's the other 2 substituents? They're not complex. At the 2 position and at the 3 position, we have what kind of substituent? Methyls, right? Yep, dimethyl. Okay. And then what's the parent name? Decane. See, look, it almost took the full page. The name. All right. Don't worry, you'll get a lot of space for these type of things. Okay. So let's do the one on the right. So the one we had on the right there. Yeah, Captain, what's up?
So would we not include the carbon attached to that oxygen?
Oh, we are in the name methoxy. So yeah, so that means we have an oxygen atom connected to a CH3 group. Yeah. Good. Okay. Let's do one last one before we have to do some quiz stuff. All right. So we also talked about this group, okay? All right. Again, we number based off the longest chain. Okay. So very similar how we named this one, except the substituents are going to be different in our name here. All right. So what about this group here? All right, we will name this as 2-methyl. There's a methyl at the 2 position, right? All right, what's the parent name of the complex chain there? So look at example above. We had propyl at the end because it was 3. What about this one? 3, right? So 2-methylpropyl. And now we're going to add that to the name. Okay. Oh, but which one do you think comes first? The methyl groups or methylpropyl? They both have methyl in there. No, because the first one runs out of letters. So that's actually the one that comes first. Ironically. Okay? Or I don't know if it's ironic, but strangely, okay? So, we have the same 2 methyl substituents. So 2-3-dimethyl. All right, -6-2-methylpropyl. Put that in parentheses. All right, decane. All right, so this fragment right here has another name. It's called isobutyl. If you were to name it that way, isobutyl would come first in the name. So depending on if you use the common name or IUPAC name, you have to change the order. Okay. when I talk more about those common name substituents, I'll let you decide which one to use. But the caveat is, some common names are alphabetized, some are not. That's where the confusion lies. So that's why I always teach it this way. Okay. All right. So, Query desk. Time for the quiz.